Okay, I guess it is time for plenary session 2 of the conference. And I understand that I'm doing the presiding. So I will say let's go ahead and get started with Professor Mark Dennis is going to be presenting first. And I'll probably do for you and everyone else who speaks what you did for me and leave you a message giving like a 5-minute warning just in case time's almost up. And I guess feel free to begin whenever you're ready. You're on mute and
Great. Thanks, Greg. And thank you, everybody, for returning to this afternoon session. So I'm very sorry that my laptop actually packed in this morning. It was what a time for it to happen. I've recovered a slightly older version of the presentation and I'm giving it from an older machine. So I hope that there isn't a crash or a delay, but I apologize in advance for that. And also I'm going to have to rush off after my talk to try and get my computer repaired. So this is the slight modified title, topological textures in optical polarization patterns, and this idea I'll talk about of Stokes origami textures. And this is work with my PhD student Kerr Maxwell. So hopefully you can see the transition. I sometimes have a problem with that. This is work that's been done partly in our Center for Doctoral Training in Topological Design at the University of Birmingham, where we use principles of topology, not only in optics and photonics, but in many different areas of physics, because obviously this, as a notion of deforming space, these ideas are very general, and ideas like skyrmions that I'll be talking about are general and apply across many different areas of physics. So in what we're talking about, we've already seen some examples of that today. We're often talking about this notion of designed versus random. So I'm using this metaphor of origami, and many apologies to Yoko and any other colleagues from Japan if my use of origami is not appropriate. As the notion of taking a flat sheet of paper and folding it up as both a metaphor and as a model for the mathematical structures that I'll talk about associated with polarization patterns. And some of what we do, whereas particularly when we're working with controlled interference via metasurfaces or holograms via spatial light modulators, is very much designed, where we're designing very complicated structures like this origami butterfly. But when we're looking at speckle patterns and other sorts of patterns, we're looking at random folding, stochastic folding, where it's just some sort of crumpled ball. And I'll use both of examples of both of those when I'm talking about structured polarization patterns today to help understand whether we're talking about something that's got a specific design behind it or whether we're just looking at random structures. And these random structures I'll talk about, or random and controlled structures I'll talk about, are both in 2 dimensions, like in the transverse plane of an optical beam that we might see, but also the 3-dimensional structures as the beam propagates and fills space. And similarly, when we're thinking about polarization, we can think of polarization in 2 dimensions, when we're varying the state of a total polarization. We might also have a 3-dimensional polarization state. For example, we built in partial polarization, although I'm not doing that here, or what I will be doing is varying the phase of the polarization. So the idea then is, when we look at at a polarization pattern, when we see, what we're really seeing is a mathematical mapping, a continuous mapping in the topological sense, from the plane parameterized by x and regular x and y to the sphere, like the Poincare sphere. And that topological mapping, although it's continuous, might have folds and other aspects associated with it. And I want to talk about today is the topology of those sorts of structures when applied to both designed and random fields. So, of course, a monochromatic light beam is typically elliptically polarized. We've seen lots of examples of that already. And we normally think of elliptic and circular polarizations as special cases geometrically. The parameter space of polarization is the Poincare sphere, of course. Our smoothly varying polarization patterns, therefore, are what in other areas of physics are called topological textures. It's this idea of this continuous mapping from real 2D space to the sphere. And whether we're looking at a mapping that covers the whole polarization space, these skyrmions, and I'll talk about those later on, or we might have a partial pattern. It's something that's trying to be homogeneously polarized but has a slight variation of polarization. What I'm proposing is that these notions are related to what could be called origami textures, which have these folds and so on. And this was a paper that Kurt and I wrote that was published earlier this year that has some of these ideas. So we have to think in terms of our mathematical parameter spaces. The Poincare sphere is a familiar one. It's in a sphere in 3D, but that 3D is an abstract Stokes space, not the real space. Our real and designed ellipse fields have polarization singularities. They map onto what are called topological defects in textures. And they carry this topology in the sense that they wrap fully around the sphere. But an important idea, which I'll come back to, is unlike many areas of topology in physics, in optics, we have no notion of topological protection. So often in other systems, there's a topological protection that forces this integer wrapping. And because we don't really have that, that's why these origami textures are quite natural. The folds are just as topological as the full sphere pattern. And so we can use this as an approach for random and designed optical origami fields in 2D and 3D. So obviously we've got the Poincare sphere, which parameterizes all of our ellipses. Northern hemisphere is well, in the optics convention, the right-handed elliptic polarized. Lower hemisphere is the left-handed elliptic polarized. The equator is the linear polarizations. And the circular polarizations are at the North Pole and South Pole. And so it's an interesting property of the sphere that if we use longitude and latitude, that parameters look like a rectangle, but we only have a single point at the North Pole and the South Pole. So this is the remarkable thing. The Poincare sphere might appear to be like a cylinder, but in fact, it's not really a cylinder. We've got just a single point capping at the North Pole and South Pole. So that's the first idea of this sort of where topology comes from in a mathematical point of view. So I'll use alpha for the azimuth and beta for the polarization ellipticity from -1 to +1. And when we do this, when we represent polarization, one of the things we're doing here, which is different from in other systems, is we're choosing what we represent. We choose to talk about the polarization parameters. We do have a varying intensity and we do have a varying phase. It's just that we normally ignore them when we think about the normalized Stokes parameters. So, for example, this surprising now or was still surprising then, originally in optics observed by Pancharatnam and then by Michael Berry, that there is also a phase that plays an important role, which we shouldn't forget, although it doesn't explicitly appear. It's an extra third parameter that goes with our two-dimensional Poincare sphere. So here's an example of a polarization speckle pattern, a 2D polarization field with ellipses. I've actually got the varying sizes as well as the azimuths and the shapes. And so you can think of this as a mathematical mapping from the two-dimensional plane to this two-dimensional Poincare sphere parameter space. It's 2x2 coherence lengths. This is a numerical simulation. The areas of right-handed from left-handed elliptic polarization, the lines where the beta equals 0 or S3 equals 0, are called L lines after John Nye's not naming them lines where the polarization is linear. And on those lines, there can be points where S1 equals 0 or S2 equals 0, which are called Stokes vortices, which I believe the first author of that paper was Freund, also Marrucci, and I think Igor Mochun and maybe Oleg were co-authors of that paper. And an important example of one Stokes vortex that's not on the L lines is where S1 and S2 are 0, and they, of course, are points of circular polarization. And they're actually points of the singularities of the azimuth alpha. They're the caps of this cylindrical Poincare representation of the Poincare sphere. So topologically, the field is a continuous map from our XY plane to the sphere as parameterized by the normalized Stokes parameters. Now, if we look at some special lines, we could look at them in 2D like I just did, or in 3D. So here's a random 3D polarization field. Actually, it's an experimental measurement. The experiment's done by the group of Miles Paget some time ago now, where we see that the lines of circular polarization here are colored depending upon their L types, lemon star, mon star, not that that matters right here. And there are also surfaces now separating the volumes of right-handed and left-handed elliptic polarization. So you can, so in this now 3D field, again, we've got this complicated mapping going from 3D to the 2D Poincare sphere, where now a single point on the Poincare sphere corresponding to circular polarization becomes a line when we think of it, what they call the pre-image, the points, all of the points that map to a single point of a given polarization. And there in that small loop, there's a very small loop that's a sort of circle, a line of circular polarization that's enclosing a loop of, a surface of linear polarization. So this topology can be rather rich and complicated. If we think about constructed fields, so this is one of the sorts of knot fields that I've developed with my group over the years, and this was experiment done by the group of Abraham Kirmi and Bob Boyd, where we embedded now these lines of circular polarization into as a knot propagating in 3D. So the pattern on the right is what the ideal the line of circular polarization should look like, a figure 8 knot, and then on the left is the experimental measurement, or reconstructed. And using polarization, these are so-called Seifert surfaces, surfaces of constant ellipticity. So you can see that we have this complicated three-dimensional topology entwined around these knot structures. So obviously we've heard of these sorts of structures for a long time now, but what my focus is now is moving away from just thinking about the special lines to thinking about what these are like as lines we just happen to choose as we map from our three-dimensional space to the two-dimensional Poincare sphere from a topological perspective. And this is where this idea of 2D skyrmions comes in. So we're returning now to 2 dimensions and design fields. And this is a field that Miguel Alonso and colleagues introduced some time ago. Several speakers have mentioned it already today, these idea of full Poincare beams, because over the entire XY plane, go all the way to infinity, it includes all of the possible polarizations. Here with a circular polarization in the middle and green. The green is right-handed elliptic polarizations. The blue is linear polarizations, and the red is left-handed elliptic, if I remember correctly. And so it captures the full sphere of polarizations, which is a sort of now a high idea of a total topological map going from the entire XY space to the total Poincare sphere. And these, so skyrmion type beams have got a lot of interest in recent years, and how they propagate and how they prepare the topology. So here's a typical example from a recent review. So, and of course, we just choose polarization because, as I said before, when we talk about optics, there are many different mathematical representations of our light field. We could use the E field, use the B field, and so on. And so the original so-called optical skyrmions, as Kostya mentioned, of the group of Bartal in an evanescent field originally, and then other groups have followed with ideas of these skyrmions associated here with the direction of angular momentum. And if we think about polarization, there's these full Poincare beams, but also these structures appear in other sorts of two-dimensional electro fields represented by Jones vectors, here in terms of polariton superfluids, and here the Glasgow group with their notion of skyrmionic beams. And the superposition in right-handed and left-handed, as we've seen a few times already today, has got a vortex in the left-handed component, so it's purely right-handed in the middle, and then you've got this little region where the right-handed wins, then the line of circular polarization where they're equal magnitude, and then the left-handed wins at larger radii. I should point out, I mean, Kostya mentioned this idea comes from magnetism. I mean, borrowed from magnetism, but the original idea actually came from this fellow, Tony Skyrm, who was actually a professor in my university, University of Birmingham. He was actually a high energy physicist. And his idea was that these skyrmions, as topological solitons, would actually describe why we get whole numbers, integers associated with nuclear physics, because in nuclear physics, all these integers in his model correspond to topological numbers. And he had a general mathematical scheme where you take the space that you're in, the space that you're describing, x in this case in a one dimension, or xy, xyz, and so on, and you map that to a corresponding version of a circle or a sphere in the dimension you're in. So this one-dimensional skyrmion is actually just a kink soliton like we see in nonlinear optics. If you think of it wrapping around the phase, you can see that we have this winding number around the phase for a 1D soliton. And the envelope is a so-called Skyrm density, the rate that's the Jacobian of this mapping from R to S1. It's the rate of change, the rate at which the phase is covered in the real space. And it's the thing that if you integrate it over the whole thing, a continuous topological charge density, it gives you 1, because these boundary conditions are, of course, fixed. And the idea is you can generalize that to any n. And that was his big idea, that so you could have he was thinking of 3D skyrmions, but you can have 2D skyrmions, and that's the case that is associated with the Poincare sphere. So the so-called Skyrm number, or topologically the degree, is what you get by integrating this Jacobian over all your original space as a continuous topological charge density. And it's a good model, as he thought, for a topological particle, and that's why they're so popular to be thought of not only in high energy and magnetism, but people look at them in liquid crystals, people look at them in cosmology, and in various other physical systems. They're characterized by an integer, which he originally called a baryon number. The size is determined by the nonlinearity, or the energy, because it's a soliton and this is this envelope size. And it's quantized, in this case, by topological protection, because in this original model, this is the whole map. It's not just choosing to represent polarization. The entire mathematical function satisfying differential equation the field variable is this topological angle. So here's a 2D version of skyrmions on a sphere. This is representing a magnetic skyrmion. And you can see there are different popular representations of wrapping a whole sphere around using 2D. So each of these is an example of an XY map to a sphere. The density in 2D is this thing involving this normalized S vector on the sphere. And these are quite, and the importance in magnetism is because these in a magnetic material will be like quantized bits for high density, low energy storage. And indeed, some of the stuff that I've done in liquid crystals and magnets is trying to realize these higher integers in these nonlinear systems. I should point out that people have spent a lot of time thinking about the generalized case that Skyrm had in mind, the 3D case. So if we map from 3D to 2D, not from 3D to 3D, we get what are called hopfions. So much of Roger Penrose's ideas in gravitational space-time physics is based on these twistors, which are in fact embeddings of this hop vibration in relativistic electromagnetic fields. And Ivo Bielynitsky-Birula has extended some of those ideas to flows of the Dirac equation. We see they're seen in liquid crystals. This is an experimental group of Ivan Smaliuk, and in magnetic multilayers, and indeed in Bose-Einstein condensates addressed by structured light. In high energy physics, these structures are all realizable. So a few years ago, working with the experimental group of Cornelia Denz, my PhD student Danica Sujic and I had the idea that maybe we could make these sorts of structures in three-dimensional beams. So I talked about this at the conference here 4 years ago, but here's just a reminder. So if I've now got a three-dimensional propagating beam, if I look at the points that map to a single point of the Poincare sphere, I get lines, these so-called these polarization filaments, and along the lines, the phase varies. And so the right-handed and left-handed C lines is just particular examples of these filamentary lines. And any 3D polarization pattern which is paraxial will have this filament structure where each of the filaments corresponds to a single point on the Poincare sphere. But if we include the phase, but think of it being normalized, the space we're in is actually a space where we've got sum of 4 squared equals 1. That is to say, a normalized Jones vector is in fact a point on the sphere in 3 dimensions. And if we think in terms of the right and left-handed circular polarization components looking like this, then they're where beta being the ellipticity, azimuth alpha, and phase gamma, then that's the natural coordinates of the 3 sphere corresponding to this hop vibration. So the beta goes from this black circle, which is the left-handed circular polarization, to this line, which is the right-handed circular polarization. I should say, this is the generalization of the Poincare sphere. It is the 3 sphere that includes both the polarization and the phase. The point is, each of the values of S3 in this 3D space actually lies on this torus. So you've got these toruses going from this circle to this, which was really a circle in the 3 sphere. So this is an underlying topological structure hidden in our polarization and phase parameters that we use anyway. So what we did was we designed a field which in 3-dimensional propagation space, combining both polarization and phase, captured this hop vibration structure. And not only do we capture the hop vibration structure, we actually captured the phase variation as you go around each of the circles as well. But I spent a long time in my introduction, but the really important part, we are all optics people. And we in optics, when we talk about objects, we're not talking about physical objects. An image of a tree is not a tree. Optical objects are images. And similarly, optical skyrmions in linear free space fields are not really skyrmions, they're images of skyrmions, just like an image of a tree is not physically a tree. What do I mean? Well, a skyrmion as Skyrm envisaged are solitons, and they're non-linear objects. But we're talking about these topological structures in free space where there's no nonlinearity. A true skyrmion is localized by the nonlinearity, whereas we design them by interference, and it's topologically protected. And because our fields can pass through 0, we don't have that either. So when I speak to condensed matter people, I use skyrmionic textures rather than skyrmions. It tends to make them less frustrated. So if there's nothing stabilizing this winding and wrapping, why not just think about the topology of the map itself without any design, just thinking about what a typical polarization field does. It can wrap around, it can cover the sphere, it doesn't have to. And let's look at that topology. So here's the random polarization pattern I thought of, that I considered before. And now let's just think of this as a piece of wrapping paper wrapping around the Poincare sphere, where each elliptic point corresponds to the corresponding ellipse on the Poincare sphere. If you wrap it all up, you get something like this. And if you unwrap it, but keep a track of what the folds, what you had here, you've got these folds where the thing folds over, and then you've got these pleats, these sort of corners called cusps. And so this is the same pattern, but now these gray lines here represent the lines which in this mapping are folded over, and the gray dots represent the cusps. So you can't see it in the XY, but if you look at the way the mapping behaves, the Stokes parameters behave at this point, you can figure out what these fold lines are, or what we call, they're the places where the determinant changes sign, the determinants of the mapping. The crease lines are a higher order derivative, where it's a sort of where the thing folds over in the image. So the fold lines, are in the Poincare sphere, and because there doesn't seem to be an established name about the pre-images, the points corresponding to this, we call these crease lines. So these are a different form of polarization singularity. They're not to do with a special given state of elliptic polarization. They're to do with a special fact that the local topology of the map folds over at that point. And the same with these cusps. So this idea of this sort of topology goes back to Hassler-Whitney from the 1950s, where he's thinking about any manifold, any surface mapping to any other surface, in general, will have these fold and cusp structures. And its generalization after the 1950s, it's what led to what we know of as catastrophe theory. So the basic catastrophe, this is as Arnold and others have classified it, the basic catastrophe, René Thom and so on, the basic catastrophe is a fold, and then that's a codimension 1 singularity, so it looks like a line in 2D, or it'd be a surface in 3D, and a cusp is a point in 2D and a line in 3D. Now we see these often from Michael Berry and other people in talking about these structures in light rays, but that's a different sort of mapping. What I'm thinking about now is the topological mapping of the polarization in a wave structure. It is nothing directly to do with rays. Should point out that whatever we see when we see structures, so like these bubbles, the outline of the bubble is the fold. And if we had a more complicated structure like this torus, we would see the cusps. These really are the structures that you generally get. Of course, this is a mapping from the 2D surface in 3D space into the plane that we're looking at. So here, what we have is our real space mapping into the parameter space. As I said, this is a plane to a sphere, where what I'm thinking about now is that these folds, if they enclose an area here, this is what we call a facet. So there's a facet enclosed by these fold lines. And if you look at what that looks like in the plane here, that facet here is actually this this pre-image of a facet, which we call a patch, and then the fold line pre-image we call a crease, and you can see these three cusps here have these points that map to the cusp that we call a pleat. So we have patches mapping to facets, we've got creases mapping to folds, and we've got pleats mapping to cusps. And so these are a form of polarization singularity. There's nothing special about the polarization state. You could rotate the polarization, you can do any sort of unitary structure. That changes the field globally. What matters here is the way the polarization changes. And so there's a lot of important information that's not global topology to do with the global winding, it's local topology to do with this particular area of the optical field. So yeah, so here is the same example. Actually, this small patch here maps to this triangular facet, and this thing here that's not much larger in XY, but it covers almost the whole Poincare sphere. And that's because there's the magnitude of the Jacobian. It's a sort of generalization of super oscillation of phase, that the area here of xy to the Poincare sphere is very, very large. And so just like we can get super oscillation, we can get this sort of super polarization coverage as well. And so this relatively small patch can nevertheless cover quite a large amount of the Poincare sphere. And unsurprisingly, this is where the intensity is small, so the polarization change with respect to XY position is large. So there's a huge amount of structure generalizing these ideas of super oscillation now to these two-dimensional polarization patterns. Here's a structured field in X and Y with a cusp. Nothing special. I've chosen horizontal polarization for the cusp point. It could have been anything. And you can see here there's an L line here, and this crease pre-image is these lines that meet at this cusp. And this is just a small neighborhood of that particular point on the Poincare sphere. And these are Stokes parameters. So this model field has a horizontal crease line, and the pleat point is at the origin, and then the neighborhood of the cusp. So what we really have effectively is thinking about this XY as it maps the Poincare sphere, giving this sort of structure in 3D. Okay, sorry. And I should say, if you zoom out, you can see that these are the origami patches. Don't worry about the middle one. And here are the L regions. And you can see that they have a similar sort of random stochastic nature. They're actually all examples of a critical percolation, which is consistent with the Gaussian random structure. And of course, that's because I've used pure speckle fields here, but possibly this percolation of these patches and creases might be a way of extracting information content down the line. I should point out that one of the reasons we justify calling these origami manifolds is actually there is a structure associated with origami manifolds in mathematics that's specifically related to what's called the symplectic structure of the Poincare sphere, so that there's a higher dimensional generalization, and this is the content of my student Kerr's PhD thesis. So we've heard of these singularity patterns, and some of us have heard Michael Berry talking about them. And if you haven't, I recommend you go to the Digital Library of Mathematical Functions, where these structures appear, the optical structures appear as a natural class of special functions, where folds are associated with Airy patterns. Of course, that's where the basis of Airy beams, and cusps are the basis of Piercy patterns, where Piercy beams come from. And there are three-dimensional cases as well, where there's not just one for 3D, there's actually three examples. Elliptic umbilics and hyperbolic umbilics show up in families of rays, but swallowtails don't. It's a slightly different underlying mathematics here. And here's the old work from almost 50 years ago of Michael Berry with John Nye and Francis Wright, where they generated an elliptic umbilic experimentally to see this triangular pattern. Again, this triangular pattern is in the brightness with the ray picture underlining it. And Cornelia Denz's group looked at generalizing those to make these swallowtail patterns in beams a few years ago. But in fact, if we're talking about these topological maps, and here's actually a paper about skyrmions in nuclear physics, you can see that they're actually here thinking about 3D structures. Here's a tetrahedral structure associated with a 3D skyrmion, and in the middle of it is this tetrahedral fold surface. And sorry, it didn't come up here, but you can see that they say here that the stable singularities can only be folds, cusps, and swallowtails. And the swallowtail is one of this 3D case because they say that 3D because these are 3D maps now to a three-dimensional three-sphere. So in optics, this would be polarization plus phase. So looking at the polarization plus phase, here's a preliminary analysis of a 3D random speckle field. And here's a small volume, this cube within it. The yellow is the surfaces of L lines, is the paraxial field, and the gray are now the creased surfaces, the pre-images of the fold. But now this is a fold in this full 3D optical hypersphere. And within this volume, this is the image. So you see the gray and the blue. I've colored to try to pick out what are the two different regions of the so-called continuous topological charge now in our 3D to 3D mapping. And in principle, one should be able to find swallowtails in there, but it's quite hard to do the analysis, and I haven't done that yet. But what I have done is able to generate in idealized fields superpositions of Hermite Gaussians in this optical hypersphere, a field which at the focal point actually is such a swallowtail point. So this is in my idealized field. This is a neighborhood of, as it happens, the left-handed circular polarization that I've chosen here. And here are two cusp lines going into a point. Here are the pre-images of the cusp, the pleat lines, and then the yellow line is not the surface of linear polarization, but where S3, sorry, that should be minus 0.9. And here, this gray is the rho equals 0. That's the creased surface now, which is the pre-image of this fold surface, and it's in 3D, this fold surface that's sort of folded over in this complicated corner. So this, I believe, is a new form of 3D polarization singularity. It's not because there's a special polarization there. What's special is the way that the field is now changing, not only in terms of the polarization, but also the phase at that particular point, realizing this swallowtail singularity. So is an experimental swallowtail texture measurable? So origami textures can and do realize these Whitney structures, and they occur just as much in random as controlled fields. There's no topological protection, so no skyrmions are stable. So this is the natural topology of these things. They don't affect the global topology, but local origami structures are interesting in design and random field textures. And a final thought, that these patches can have any area you like at all. So maybe if we are to extend some sort of analogy, they're not just 4 pi, they can have any area. So maybe these are a version of polarization anyons. So I thank you for your attention, and I point out that this origami butterfly was in fact a swallowtail butterfly. Thank you very much.
Thank you very much, Mark. Do we have any questions? We have a few minutes for a few questions.
I have a question.
Yep, go ahead.
Very nice talk, Mark. Yeah, lots of things to think about. One of them is when you talk about your going to the three-dimensional patterns, the swallowtails and the umbilicus, you did it by thinking of these three-dimensional, well, the three generations here. Would another way to do it would be just looking at propagation? Say if you look at how you're covering the sphere and then that evolves as you propagate the field, and you'll see these cusps and merging, and then you would also see these three types of singularities.
So well, you wouldn't see the three types. So it's to do with, I mean, it's a slightly technical thing to do with how many different control parameters you have. So when you're thinking about elliptic and hyperbolic umbilicus, those really are two parameter families of surfaces. Whereas the swallowtail is really it's like a 3D to 3D.
Okay, so that one is.
It's a mathematical. So what Cornelia's group did, they managed to realize it, but it's not a generic singularity in the way that elliptic and hyperbolic are.
It's
but
something
yes,
you have to construct.
So
yeah.
have in general these as the thing propagates, very complicated networks of these pre-images of cusps. Now you don't have to just look at phase. I've looked at phase because it has this nice optical hypersphere, but you could, for example, look at these where the degree of polarization is varying with position as well. And you could look at those structures as well. These are just the natural these are the natural structures that function, topological structures that function, continuous functions realize. That was why catastrophe theory was such a big thing in the 1970s.
All right, thank you.
All right, we had one hand raised question. We have time for that last quick question before we move on.
Hi, Mark. It's Albert speaking. Okay, I agree with Miguel. It's been a wonderful talk as usual. I'm very happy that you clarify at last what the proper use of the Skyrmion name is, because I've seen the inflation of using of the use of the Skyrmion, when in fact, when you go to the original paper, you realize, as you mentioned, that this, if you really want to have a real Skyrmion, we have topological protection, you need to have nonlinear solution. And definitely you cannot agree that you cannot get this using Gaussian beams or the standard beams we use that basically vanish at infinity. So they are linear, actually. So my question is, it's clear that nonlinearity is a way of generating the conditions for stability, like in the models you mentioned. But my question is, it would be possible that controlling boundary conditions artificially from outside by keeping it, forcing the solution to be always with the same boundary condition, which is required by your solution, it will be also making the same job for stabilizing the solution. So that would be playing with boundary conditions. Instead of doing dynamically, you do it externally, so to say.
Right, so that's so it's a good suggestion. Of course, that can be done, but the real thing that guarantees the topological protection is the fact that the thing cannot go through zero. So what you really need, so the boundary conditions can do some job, but from a topological point of view, the thing you really want to do is to stop the variation of the intensity. You want these to be as S0 flat as you can.
No, that's what I mean. I mean that you keep artificially from outside the field different from zero at the boundary. That's the point.
Yeah, but it wouldn't just be at the boundary, it would be everywhere in the field. Every point in the field, every pixel. So I don't quite understand how that can be a boundary if you're saying every pixel inside the field has to be the same intensity.
Imagine, for example, a set of spins, and you force the spins in the boundary to be all the time using an external magnetic field this way.
That's what the magnetic skyrmions are. They are spins because you don't have any magnitude. But if you're trying to do this with an optical field, even if it was a non-linear optical field, you have to have a normalized intensity if you want to have a topological solid top.
Sure. No, I agree. I was just wondering if there would be an alternative just to.
It might, certainly there are exotic atomic materials that allow that. But I'm saying that, but I'm saying that we shouldn't stop using the term skyrmionic texture. We just have to be careful that these aren't skyrmions in the topologically protected sense. But then I'm suggesting that the appropriate topology then is by thinking about these more local folding and custom structures.
So please use a Skyrmion texture or a Skyrmion-like instead of a Skyrmion. So it's less misleading. So, okay, thank you very much.
Okay, thank you. Let's move on. I believe we have Professor Wang next. If you're there and you're ready to share your screen and present.
Can you hear me?
Yes. And we can see it. Feel free to start the, yep.
Yeah, okay. Good afternoon, everyone. I'm Wang. Nice to see all the friends from all the world. Okay. And first of all, thanks the conference chair for the nice, kind invitation. As shown in this, the title of my presentation today, I would like to talk about the matrix direct correlation of the vector electric fields and its application to unification of coherence and polarization of light. Okay, I'm from Harvard University of UK, and Professor Mr. Takeda is from the Autonomia University of Japan. Okay. This is the outline of today's talk. Okay, first, I would like to show you the polarization sensitive interference law. So through the two types of the Young's interferometer, we would like to measure the mutual coherence matrix and the generalized Stokes parameter. Then next, we will move on to the polarization coherence tensors of stochastic electromagnetic waves. So in this second part, I would like to introduce the characterization of various polarization coherence phenomena. Okay, then we will just go to some details of the temporal coherence tensors, and it's just the measurement and the applications. And I will also talk about the spatial coherence tensor and its measurement. Okay, for the last part of my talk, it's about the partially polarized light. Okay, in this session, I would like to introduce the two geometrical representations of the polarization matrix and the Stokes vectors for partially polarized light. So first, let's go to the first topic, of today's presentation, the polarization sensitive interference law. As you see in this just figure, this is the typical, just Young's interference. But just compare with the conventional one. Here we have taken the vector nature of the light into account. And we have the source, and after source we have the the opaque screen with the double pinholes, and we also have the detection just a screen detection plane. Compare with the conventional Young's interference. Here. We have placed, the several linear polarizers, after the pinhole and also before the viewing screen. And by changing the orientation of the by changing the transmission axis of the linear polarizer for this linear polarizer, we are able to polarization filtering for the incident beam. And the last linear polarizer just before the viewing screen, that is the linear polarizer of the 45 degree. So for all the incident beam, we are also able to just make a projection and just pass through all the light for the interference purpose. And at the detection plane, we are able to observe its just the fringe pattern. So through this kind of, just a structure, we are able to write this, the equation. Here shows the equation for the polarization sensitive interference law to measure the mutual coherence, just the matrix. Here, as you see, the first term represents the intensity at the detection point Q. From the light, for the light from the pinhole of P1, and the second term is the intensity at the point Q, at the detection plane, from the pinhole P2, from pinhole P2. So therefore, the subscript 2 represents the pinhole P2. And the final term represents the cross term between the two beams. So that is exactly the elements of the mutual coherence matrix. Through this way, we are able to just to upgrade the conventional Young's interference for measurement of the mutual coherence matrix. So this is one way to detect the polarization coherence of stochastic electric fields. And this figure shows another way for the polarization coherence measurement. Basically, it is just Young's interference again, but here, instead of inserting the linear polarizer behind the the pinhole, here we just choose a different method for the measurement. Here at the detection plane, we insert different just the combinations of linear polarizer or quarter wave plate. Therefore, once we have this fringe, okay, we are able to just to observe the fringe in terms of the Stokes parameter. So it means that at the detection plane, what we observed or what we measured is the Stokes parameter instead of the intensity itself. So here, the intensity has already been polarization filtered. Okay, so after straightforward, okay, we are also able to write another polarization sensitive interference law in terms of the Stokes parameter or generalized Stokes parameter. As you see, the first term represent the Stokes parameter from the contribution of the light from the pinhole P1, and the second term here represent the Stokes parameter from the contribution of the light of the P2. Okay, and the last term represent the generalized Stokes parameter for these 2 points this is just a generalized Stokes parameter. Okay, so through this way we are also able to measure the polarization coherence for the stochastic electric fields. So these are 2 different type of the scheme for the measurement of the polarization related coherence phenomena of the light. Now let's just come to a more theory about the polarization coherence tensors of the stochastic electromagnetic waves. Okay. As you see, okay, before we just show you, okay, the measurement of the mutual coherence, matrix, okay. So basically, to characterize the polarization coherence phenomena, we are able to write the electric mutual coherence tensor in this way. So this is the gamma, okay. This is the gamma. Basically, this gamma is the time averaged optical fields at different spatial temporal points, P1 and P2, with the time delay with time delay of tau. So as you see here, this is the chronic product. This is the chronic product of the electric field, electric vector. Okay, electric vector. So once we have the chronic product of the electric fields at 2 different spatial temporal points, and we also have the time average, as you see from the angular bracket. This means that it indicates the time average. So this is once we understand this definition for this mutual coherence matrix, okay, we can see that there is another way of interpretation for this definition. That is the matrix direct correlation of the vector of the electric vector. So in this way here, we just follow, as you see, we follow the chronic product, because chronic product is the matrix, the direct product. So here the star represent the correlation. A star, usually we often use a star represent the correlation, and the circled star represent the chronic product. So the combination of the circle and the star will give a new notation for the matrix direct correlation. So in this way, okay, we can understand the mutual coherence matrix as the direct correlation of the electric vector at the 2 different points, P1 and P2, with the time delay of the tau. And this, as you see, this is just a matrix, okay? But meanwhile, we can also decompose this matrix based on the tensor way. So in this way, okay, we see that for each element of this matrix, okay, can be represented as the coefficient of the tensor basis. Here, EMN represent the tensor vector or the basis vector. So as you see, for these 4 basis vector, they are orthogonal and also orthogonal to each other, and also they are normalized. normalized. So this just for just tensor just basis vectors, okay, span are just 4-dimensional Hilbert space to measure this mutual coherence tensor. This is just one way to represent the polarization coherence phenomena. Okay. Meanwhile, okay, once we see that we just represent this mutual coherence tensor in this way. Okay, we know that similar to the vector. Vector has its direction and also has its magnitude. Similarly, for the tensor, we also have the magnitude of the tensor and also have the direction. So therefore, these four just orthogonal just base vectors serves as the direction, provide direction of this tensor, and the magnitude of this matrix. Okay, here we use the let's say use the Frobenius norm to represent this just a tensor magnitude, to represent the magnitude or length of this tensor. So once we understand, we have this geometrical representation or geometrical interpretation for this tensor. Okay, we are able to define the tensorial complex degree of mutual coherence. As you see, this is the definition for the tensorial complex degree of mutual coherence. So here we use the Frobenius norm for this, the polarization matrix at each point P1 and P2 as our normalization, for our normalization. So through this way, okay, we see that this tensorial complex degree of mutual coherence, okay, has 4 components. Here the gamma represents the 4 components, and meanwhile this E, okay, E hat represents the base vectors, okay, and so therefore this just tensorial complex degree of mutual coherence, okay, provide just a measure of the degree of the similarity of the electric magnetic field at the two spatial temporal points. So once we have this tensorial complex degree of mutual coherence, so we know that we see that, okay, this the Frobenius norm of this tensorial just a complex degree of mutual coherence, okay, is bounded within 0 and 1. Once the gamma is equal to 0, we just call this light as the incoherent light. Once this gamma is equal to 1, we call this light as the coherent light. As this is just have the good correspondence with the scalar case, scalar light. And besides, the mutual coherence tensor, okay, just before we see that, okay, the generalized Stokes vector, is another way to represent the polarization coherence phenomena of light. Okay, so through this way, as you see, we can rewrite the generalized Stokes vector in this way. Once again, here we have the the conic product of the 2 electric field. This is one, and this angular bracket represents the time average for infinity time average. Here A is the transformation matrix shown here. A is here. Okay, through this way of just the mathematical definition, okay, we see that the generalized Stokes vector can be considered as the as you see as the matrix direct correlation of the 2 just electric fields at the 2 different points, P1 and P2, and here A serves as a linear transformation. Okay, so once we write the generalized Stokes vector, okay, so this generalized Stokes vector is the 4 times 1 with a dimension of 4 times 1. So therefore, this generalized Stokes vector also has the vector base base vectors. Okay, here E0, E1, E2, and E3 are the orthogonal and just normalized base vectors to span in the 4-dimensional Hilbert space. So see, this is just another way to represent the polarization-related coherence phenomena of light. So once again, if we use the Frobenius norm of this just Stokes vector, at a 2 point P1 and P2. Okay, we can use this forbidden norm, okay, for the normalization. Therefore, we are able to define introduce the vectorial complex degree of Stokes vector. So in this way, this vectorial complex degree of Stokes coherence, okay, also has 4 components. Okay, here the gamma SL serves as the components, and the EL serves as the orientation. That is base vectors, and so this vectorial complex degree of Stokes coherence also bounded so within 0 and 1. When gamma S equal to 0, this forbidden norm is equal to 0. We call this light as the incoherent light. When gamma S is equal to 1, we call light as the coherent light. So through this way, okay, based on the just the geometry representation of the Stokes vector for normalization purpose, we are also just establish another or just alternative way to represent the polarization related coherence phenomena. Okay. Since because this is just as we see mutual coherence tensor and the generalized Stokes vector, these are both can be used to represent the polarization related coherence phenomena. Okay, of course, there are just a linear relationship between these 2 different ways of representation. Here shows the linear transformations between these 2 tensorial representations. As you see, okay, from the component of the generalized Stokes parameter, okay, we are able to represent the mutual coherence tensor in this way. So this is gamma is the mutual coherence tensor can be written in this way. Here sigma L is basically sigma naught is the identity matrix. Sigma S1, S2, and sigma S3 these are just the polyspin matrices. Okay, this is the well-known representation. This is one way for to give the link. Okay, between the mutual coherence tensor and the generalized Stokes vector. Okay. Meanwhile, okay, so we can also represent the generalized Stokes parameter with the aid of the elements of the mutual coherence matrix. Here is another way. As you see, so the generalized Stokes vector S can be represented as the elements of the mutual coherence matrix. Here we also have the just sigma mn. Sigma mn is just a vector. Okay, through this way, as you see, this is just this way we can also establish the linear transformation between these each other. So from this kind of expressions, we can understand that both mutual coherence tensor and the generalized Stokes vector can be used to represent the polarization related coherence phenomena. So okay, so each way will be okay because they are both equivalent to each other, just based on the requirements of your interest. Okay. Now let's just come to a little bit more just the steps further about the temporal coherence tensor. Okay, see here. Okay, see here. Once we talk about temporal coherence, it means that okay the position as spatial point should be at the same position. So okay, so now okay, our just the temporal polarization coherence tensor can be derived by setting the P1 equal to P2. Through this way, we are able to have the temporal polarization coherence tensor in this way. So in this way, so this here P are the same, position are same. So similarly, we also have the tensorial complex degree of self-coherence. It is once again, it has been normalized by the forbidden norm of the gamma at the equal time. Equal time means that the tau time delay is equal to 0. Okay. And in a similar way, okay, we also have the temporal Stokes vector. Temporal Stokes vector is in this way. So it is just put the P1 equal to P2. We are able to write it in this way. So we also have the vectorial complex degree of Stokes self-coherence defined in this way. So through these just definitions, we can quickly recognize that the concept of temporal polarization coherence has to do with the ability of the stochastic electric field to interfere with a delayed version of itself, because at the same just spatial point P. So it's just a delayed version of itself. So this is the physical just meaning for this temporal polarization coherence tensors. Okay, now we just show you some relationship between the temporal coherence tensors and the polarization polychromatic source. So as you see in the left side figure, okay, as we know that for point source with a broadband spectrum, okay, at each different just frequency, okay, they may have a different polarization states. So and the right side shows the temporal coherence tensor. Okay, so in a similar way as the well-known Wiener-Khinchin theorem, okay, we are also able to establish the Fourier transform relationship between the spectral tensors of the source and the temporal coherence tensors. So this is the just a tensor version of the Wiener-Khinchin theorem. Okay. So as you see, this is a Fourier transform relationship. Okay. Now, the question will be easily raised that is it possible for us to to measure the temporal coherence just tensor and also to reconstruct the polarization sensitive spectral distribution of the source? The answer is yes. Okay, here as you see, we come to we just let's read first recall the conventional Fourier transform spectroscopy. Okay, this is the microsome interferometer. Okay, here by changing the optical path difference through the moving mirror, we are able to just measure the let's say the coherence function. This is for the scalar case. Okay, in order to measure the polarization Fourier the spectroscopy. Okay, here at the before and after the sample. Okay, we insert the two sets of the polarizing filters. Okay, the first one before the sample. Okay, we try to modify the incident beam illuminating the sample. And after light pass through the sample, okay, just before the detector, we also introduce a different set of the polarizing filters to detect the it's just a Stokes just a distribution. So in this experiment, okay, we use polystyrene as our sample because this is just a sample has a biorefringent just properties of this sample. So we try to change try to just see how does the polarization related spectrum changes once we through this measurement. And this is there stick ball models of this kind of material. Okay, so here shows the details of this just experimental setup. So basically, this is the white side, the white part is the conventional, just Fourier and just infrared Fourier transform spectroscopy. Okay. Inside the chamber, okay, we have made some kind of modification, as you see through the sandwich structure. So the light is start from the right hand side and illuminate. Okay, so the first two parts, okay, can be used to modify the incident beam, modify the polarization state of the incident beam. And here is the sample. Here is the sample, this sample plane, and this is another, another polarizing filters for the detection of the Stokes parameter. And here at the end, okay, we have the infrared detectors. Okay, infrared detectors. Okay, as you know, for the let's say for the white light, for the broadband light. Okay, usually let's say the quarter wave plate does not work, or it means that to achieve the circular polarization it's not easy for the broadband light. So in this way, okay, so we particularly ordered just a chromatic quarter wave plate from a German company. So within this very wide range from the 2.5 to 7 micrometer, okay, this just device almost can achieve just a good, quarter wave just a phase delay for this very broadband. Okay, so once we have this, we modified this spectroscopy. Okay, now we are able to have our measurement. So this show you the example of the one set of detected fringes for the reconstructed spectral Stokes vectors. Okay, so here, as you see, here we have IX, Y, I45, I135, and also I just in left circularization and the right circularization. So this is other fringe patterns. Okay, so through the definitions between the, let's say, through the definitions for the Stokes parameter, okay, we are able to transform this intensity distribution to the Stokes distributions. Okay, then after applying the Fourier transform, okay, we are able to reconstruct the spectral Stokes vectors for this polystyrene. Okay, so here, as you see, this is the experimental result. Okay, each column represents the spectral Stokes vectors. Okay, each column represents spectral Stokes vectors. Okay, each column, and once we modify the different that's the light for the illumination, we have the different. Reconstructed spectral Stokes vectors. So through this result, okay, we are able to reconstruct the desired spectral transmission matrix for this particular sample. So here is the reconstructed spectral transmission matrix for the polystyrene. And from the spectral transmission matrix, okay, we can also, reconstruct the spectral absorption matrix for this material. So from this figure, you can quickly see that, as expected, this sample polystyrene do have the birefringent effect for each different spectrum distribution. So this is probably the first demonstration of the polarization Fourier spectroscopy. Okay, now let's see. Besides the temporal coherence tensors, we are also interested for the measure of the spatial coherence tensors. Okay, so now let's see in this way. Once we talk about spatial coherence phenomena, okay, we often set that time delay tau is equal to 0. So in this way, okay, we have the mutual polarization tensors, okay, can be derived by setting tau equal to 0. So this is this is the definition for the mutual polarization tensor. Similarly, okay, we also have the tensorial complex coherence factors in this way. So once again, here the tau equal to 0, we arrived at this tensorial complex degree or complex coherence factors. And in terms of the generalized Stokes parameter, we also have the mutual Stokes vectors. We have the mutual Stokes vectors. Okay. Okay. So can be defined in this way. Okay. So these spatial coherence tensors indicates the ability of the electromagnetic wave of the two spatial points, okay, to interfere when average over time. So through this kind of definition, you can quickly understand the underlying physics indication, physical indication of this spatial coherence phenomena. Okay, so this is a relation between the spatial coherence tensors and the polarization source. Okay, so basically we have an extended source. Okay, we are in the far field. We have the mutual polarization tensor, or mutual Stokes generalized Stokes tensor. Okay, so once through this kind of geometry, we can quickly see that this equation, this equation represent the tensor version of the fan theta Zernike theorem. Okay, so basically for the source, okay, no matter we use the source, we represent it as the polarization matrix or the Stokes vectors. We are able to to relate this source distribution, okay, to the far field, the coherence phenomenon in the as a Fourier transform, a matrix-based Fourier transform relationship. Okay, this is the relation. Okay, and let's say here, let's just go to one more step to see how can we just measure the spatial coherence tensor. This shows the proposed setup. Basically, this is the radial shearing, polarization sensitive radial shearing, interference. Okay, so once here for this just two beams, we introduce different radial shearing. And after for each beam, okay, we select the different polarization states. And before the detection plane, we insert another linear polarizers, okay, after 45 degrees. So through this way, after both light, okay, just interfere to each other, and at the detection plane, we are able to have this, the final intensity distributions at the detection plane. So this shows you the result. So the first term shows the intensity contributed from the first beam, okay, with the radial shearing of alpha 1, and the second term shows the intensity distribution from the second beam, second arm of the interferometer, with its magnification or radial shearing of alpha 2. So therefore, in the cross term give us the, let's say, the mutual coherence tensors. Okay. So see, this is just the experimental setup, and here in the bottom, I just show you, just 4 frames of polarization, dependent, fringe distributions. Okay, this is for IXX, IXY, IYX, and IYY. Okay, so as you see in this just 4 fringe patterns, okay, the fringe contrast has been expressed in terms of the position, okay, in terms of positions. So by applying the Fourier fringe analysis technique, we are able to reconstruct the spatial coherence tensor. So here shows the result. So the left side gives you the amplitude, the right side gives you the phase. This is the reconstructed tensorial complex coherence factor. Meanwhile, we can also, just reconstruct the vectorial complex Stokes coherence factors in a similar way. So here shows the result. So as you see, both just can be used to represent the spatial coherence, but the elements have a different, distribution. Elements have a different distributions as expected. Okay. Although, let's say, mutual coherence tensor and the generalized Stokes vector have a different distributions for each element. But the Frobenius norm for this the complex degree of tensorial complex degree of coherence have the same structure. In our experiment, our sample has the circular pattern. So it means that after Fourier transform, we have the Jink pattern for this coherence distributions. So as expected, the Frobenius norm for the tensorial complex degree of coherence, okay, has this typical Mexican hat structure, Jink structure. Okay, so in this talk, okay, I have just show you, different, definitions for various measures of polarization coherence tensors. Okay, once we choose, okay, the EMN, okay, as our basis vectors, okay, we have the one set of representation. Once we choose EL for L equal to 1, 2, 3, okay, we have another way to represent the polarization coherence phenomenon. So in this way, okay, so these two different ways are quite equivalent. So it is based on our choice to characterize this phenomenon. Okay. So once we, let's say, talk about the coherence phenomenon, the last part, okay, I would like to come to the partially polarization of light. Okay. We know that, okay, when we know that the partial, let's say, polarization is a type of the correlation phenomenon, okay, at the single point with the equal time. So in this way, okay, the conventional polarization matrix or polarization tensors can be defined in this way. As you see, the same position correlation with the equal time. So the equal time means that the time delay is equal to 0. So therefore, the polarization is an equal time, same position correlation phenomenon. So in this way, we also have the normalized polarization tensor that is normalized by the Frobenius norm of this polarization matrix. Okay, so we have this normalized polarization tensor. So the degree of polarization can be defined in either way, or through the polarization tensor J, or through the just normalized polarization tensor J hat. Meanwhile, noting that the polarization tensor or polarization matrix is the emission. So it means that JXY is the complex conjugate of the JYX. Meanwhile, this is an emission matrix. Meanwhile, we also know that the normalized polarization tensor has the Frobenius norm equal to 1. So we will have this, ellipsoidal equations. So through these ellipsoidal equations, we can represent various type of states of polarization for partially polarized light. This is a much advantage than the let's say conventional Poincare sphere, because Poincare sphere can only be used to represent the fully polarized light. But here the let's say the ellipsoidal structure can be represented as various states of polarization. As you see here, this just the point. The point U represent the unpolarized light. At this location. Here, the arc on the ellipsoidal surface, okay, represent the fully polarized light with the degree of polarization P equal to 1. So the point H represents the horizontal, just the polarization, and the point V represents the vertical polarization, and the point D, okay, there are several different, states of polarization occupying the same position, such as the point D. Point D, as you see, for the linear polarization or elliptical polarization with its main axis along 45 degree or 135 degree, they share the same position on this ellipsoidal surface. As I said that, okay, this arc line represent the light of the completely polarized light, and U represent the unpolarized light. So within this boundary, that's the point for the partially polarized light, for the partially polarized. So this is the one way of the geometrical representation for the polarization matrix, And similarly, okay, we can also provide another geometrical representation of the Stokes vector. As you see, the Stokes vector is the Stokes vector. Okay, thank you. Yeah. Okay, I will finish soon. Okay, so the Stokes vector can be just can be written in this way. Okay, so now we can just rewrite the Stokes just vector into two parts. The first part is is the Stokes vector for the, let's say, total intensity. The second part is the Stokes vector for the totally polarized component. So we also have the normalized Stokes vector. Through this way, okay, the degree of polarization can be redefined in terms of this Stokes vector or normalized Stokes vector. Okay. So now after introducing the hyperspherical coordinate, okay, we can represent the Stokes vector on this hyperspherical dome. Okay, as you see, So this is the four-dimensional, sphere, hypersphere. So we choose the E naught as the one the axis, and another three axes can be used as the E1, E2, and E3 for the Poincare sphere. So in order to visualize this hypersphere, we use the projection method or slicing method. So by slicing along the E1 axis, we are able to achieve various Poincare sphere with a different radius. At the north pole of this hypersphere, that is the unpolarized light. And at the bottom just a slice that gives you the fully polarized light. So each slice just give you the three-dimensional Poincare sphere. So here the dome itself represent the four-dimensional hypersphere dome. Okay. So due to time, probably I have to stop here. Okay, so this is the conclusion of my talk. So basically, through this talk, we've tried to give through the matrix direct correlation and the, let's say, two sets of orthogonal basis vectors. Okay, and we try to develop the unified tensorial theorem and experiment for coherence and polarization of light. That's the end of my talk. Thank you.
Thank you very much. Does anybody have one quick question before we move on? Okay. Well, thank you again.
Thank you. Yeah.
And we will move on to Professor Marrucci's talk. If you've got you're here, and you can go ahead and share your screen and go ahead and get started.
Let's see. Okay. Just a second that my I will need to quickly get out of Zoom and get it back in. It's the first time I'm using Zoom since a new computer. So just a second.
Okay.
Okay, here I am again. Let's see if the sharing works. Yes, should work.
Yeah.
Okay, do you see my window?
Yes.
Okay, so let's start the sharing. Thank you for introducing me. Thanks to the organizer for inviting me to this conference. Today I will talk about photonic quantum circuits in free space using structured light. What I will present is mainly an introduction to the concept of photonic quantum circuits, and then present some work in progress that we are doing on this topic. Let me start with this introduction of photonic circuits. I also start the timer. What are photonic circuits? Photonic circuits are essentially linear operations on a set of optical modes. Suppose you have a discrete set of optical modes. Any kind of modes will do. I will discuss that in a moment. And then any optical field can be represented as a linear superposition in complex space of these optical modes. So you can represent it as a vector of components, and then a photonic circuit can be seen as a matrix of connection based on a set of linear operations that connects a set of input optical modes with a set of output optical modes. So, for example, the third optical mode in this example will correspond to a given linear combination of all the input modes in general. The matrix that defines this connection somehow defines this photonic circuit. In addition to connecting the input and the output modes, there may be light scattered out of the system in general. And so the most general situation is that you have this matrix, but somehow there is also a connection. Somehow there is a loss in the form of light scattered out or absorbed, for example. There are many examples of realization of this concept aimed at essentially implementing, using a photonic approach, for example, matrix vector multiplication, general matrix vector multiplication. So in this paper that I'm reporting here, I am citing here, this was based on a silicon slab with the modulated silicon height that somehow implemented an arbitrary matrix vector multiplication, arbitrary but not reconfigurable, somehow written in the structure of the system. If you don't have light scattered out of the system, so all the light is somehow, all the energy in the modes stays within the set of modes that you define your system, then the matrix becomes unitary and therefore obeys the standard unitary matrix law that is shown below, that the inverse of the matrix is the same as the adjoint. Implementation of an arbitrary unitary transformation among optical modes can be achieved using a set of beam splitters and phase shifter, as was first demonstrated in this paper by the Zeilinger group back in 1994. And this is between separate path mode. This image in the upper. Let me see if I can use a pointer somehow. Yes. Okay, this image up here shows the same concept. Each beam splitter is coupled with a phase shifter from one side and another phase shifter from the other input port. And then this defines a set of parameters by which you can somehow control your unitary transformation so as to have an arbitrary unit transformation. The same concept can also be achieved in an integrated approach, for example, using waveguides, as shown in panel B, and the concept is similar. The waveguides can define beam splitters by having two waveguides coming close together for a while, and then you can have phase shifter to control the transformation. Several papers have appeared, especially on this integrated photonic circuits approach, in which you could have, for example, this universal linear optics in Science in 2015. More recently, this was used for photonic simulation, this in 2017, using again a set of beam splitter in an integrated approach. Let's move on to quantum photonic circuits. In the case of quantum photonic circuits, the concept is essentially the same, but you work in a quantum regime so that the modes somehow carry one or few photons, and this allows you to do essentially some primitives, some basic protocols of quantum computation. For example, this device that is shown in this figure was published in Nature Photonics in 2023, and is a very large-scale system integrating about 2,500 components, including both generating photon pair sources, multiple photon pairs, and then this mixing based on the concept that I just described, and finally detectors. What you can prove and was used for proving with this kind of approach is a specific kind of computation, which is so-called boson sampling. In boson sampling, essentially, you have this large matrix connecting the input and the output, And then you measure, you use these experiments by sending in a certain number of photons and detecting the frequency by which they appear on the output modes. And then using that measurement, you can estimate the so-called permanent of the matrix, which is essentially the same as a determinant of a subset of the matrix, except that all the minus signs of the determinant becomes plus, so that everything is positive. And this strange combination of matrix elements is actually not very useful in general, but it's very hard to compute. So to being able to estimate this permanent in a large matrix using this approach allowed this method to demonstrate for the first time somehow very large a computation of very high complexity in computational terms, possibly higher than classical methods for computation. So somehow it was a way to demonstrate the so-called quantum advantage for the first time. More technical, this calculation is a class P hard problem. And this is an image from a paper in Science of 2020 in which using this approach based on boson sampling, somehow, I guess the first quantum computation advantage using photons was demonstrated by the Pan's group in China. And this was using 100 input and output modes, and I forgot how many photons at the same time. Now, what I showed so far was talking about modes, but only showing somehow modes that correspond to separate spatial paths of the light. But you can also use approaches in which the modes are not separate paths. And you can talk sometimes about these concepts using the concept of synthetic dimensions. So in general, you don't need to have optical paths, which is of course the most straightforward approach to having a set of discrete set of non-overlapping modes, orthogonal modes if you want. If they are orthogonal, the advantage of having orthogonal modes or non-overlapping modes is having no crosstalk unless you want the two modes to talk to each other in general. But you can achieve that using, for example, instead of distinct spatial path, you can use distinct temporal modes like time beams, in which the separation is temporal, but all the light travels in a single beam. And this can have distinct advantages in terms of practical management of this system. You can also use entirely overlapping but orthogonal transverse spatial modes. Again, in this case, you have that all the modes travel in the same beam, essentially, but they are defined by orthogonal spatial modes. And this somehow is the interaction, the intersection between this topic and the topic of structured light, because structured light is mainly focused on using and studying and exploiting transverse spatial modes, although not only spatial modes, but mainly spatial modes. And this is also the approach that we have taken so far. So let me discuss more in detail our group approach to photonic circuits. Once again, the concept is to have a set of input modes, a typically unitary transformation in our case, although more generally can be an arbitrary matrix, and a set of output modes. We often do experiments in which we start from only one mode or maybe a few neighboring modes, but of course our approach is not limited to that. We often describe this unitary matrix as the result of a so-called quantum simulation. So essentially our matrix describes a physical system that is similar to a simple quantum system with given a Hamiltonian, so that our unitary matrix is somehow the exponential of that Hamiltonian. And of course, we have also the interest of using this to do in the quantum simulations, to mimic these quantum systems and learn something about them. But more recently, we are using this essentially as a proxy for getting to the concept of quantum circuits. So one of these possible quantum simulation is the quantum walk, which is somehow a prototypical quantum dynamic process, which is the quantum analog of the classical random walk. In the classical random walk, you have a walker, which can go, for example, left and right at random in time. In the quantum random walk, you have that the same walker can, since it's a quantum object, can go both left and right in some sense. It's described by a wave function, which has amplitudes for both going left and going right. So it will go everywhere as long as it's not measured. And only when you finally measure the position of the particle, of the walker, you will have a statistical distribution similar to the classical random walk. The difference is that in this second case, the quantum case, you also have interference between different possible paths leading to the same position. Although the quantum evolution before the end, before the measurement is done, is entirely deterministic. The wave function evolves deterministically, but true randomness occurs when measurement takes place. So why quantum walks? Quantum walks have been proved to be usable in principle to do universal quantum computation. So any possible quantum computation can be framed in the form of a quantum walk. And they are also quite useful for doing specific kinds of quantum simulation, for example, to simulate transport phenomena or certain classes of topological physics. So we try to develop our system as essentially unitary mode mixers, and our black box doing the unitary evolution is a quantum walk in a sense. How do we implement them? To implement a quantum walk, you need certain resources. You need an n-level system to represent the walker. It doesn't need to be an actual space coordinate. If you want the quantum walk to be discrete, you want an n system, an n-level system, but these levels can be any kind of quantum system, or as long as they are somehow orthogonal to each other. N should be large enough to describe a long-lived quantum walk, of course. In principle, it can be also infinitely large. Then you need a two-level system to represent somehow the coin that is tossed to make the random choice. In the random walk, you can think that the random choice is corresponds to the toss of a coin, and then depending on the outcome, you go left or right. In the quantum system, you need the two-level systems on which you perform certain quantum transformations, which are the correspondent of the quantum toss coin tossing, and then that determines the evolution of the walker. You need an evolution operator that is a coin-dependent translation. So depending on the outcome, on the level at which the coin is found, the walker will shift right or left. And finally, you need an operator that somehow rotates the coin state, the two-level system coin state, which is the equivalent of a coin tossing. Our implementation, first of all, let's start with the coin, which is the simplest thing. Our coin is polarization, which is for light a very convenient choice of coin, because it's two-level. It says two-state actually rather than level. Usually they are the same energy. Two-state system. And as we shall see, it's also very easy to use it to determine the evolution of the walker. So we use optical polarization for coin, and we usually use left and right circular polarizations for the two coin sides, because it's convenient for our approach. For the walker, we initially were using, in our first works, 2015, 2016, 2017, we're using orbital angular momentum eigenstates. which are essentially electromagnetic waves having a spatial structures that includes this phase factor here, in which besides the plane wave term has also this azimuthal phi dependence with an integer m, which is an integer that has any positive or negative value. And depending on this value, you have a helical wavefront resulting from this equation. The helical wavefront, so we'll have, if you have m equals 0, actually is a plane wave. It becomes the simplest case of a plane wave. But if it's m non-zero, you have a helix. If m is equal 1 or minus 1 is a single helix with right-handed or left-handed handedness. If you have a higher m, you have a multiple helix with the same handedness, but multiple with the number of helices that depends on the absolute value of m. And then you have these phase structures, intensity structure, and so on. This was our first approach. It was very natural because we were working on orbital angular momentum, and also because this is a natural choice for a one-dimensional discrete set of orthogonal modes. But nowadays, more recently, we have shifted to a simpler momentum encoding, which is based on the following. Suppose that you call 0 just a single plane wave traveling along z. Then, let's suppose this is z direction. Then you can add a small phase dependence along x, which correspond to tilting slightly the plane wave. Or you can add twice as much of a phase gradient along x, and you have a higher tilt of the plane wave, and so on. You see that I'm taking integer multiple of a delta k for defining this phase gradient. Now delta k, which you can also set it as 2 pi over a transverse period, the spatial period lambda, capital lambda, can be any value, because in principle there is no discretization in this set of modes that we are defining here. But we can keep it fixed artificially so that we somehow select a set of orthogonal modes which is discrete. Although in principle the plane waves could be continuous, we select a subset which is discrete, artificially discrete. Delta k is taken to be much smaller than the k itself, which corresponds to saying that these tilts are very small. Also that capital lambda is much larger than the wavelength. And this is needed because otherwise you should take into account that k is actually slightly reduced. Otherwise you have to change the frequency. And so in our case, for example, typical values of capital lambda are in the order of centimeters, or at least several millimeters, while lambda is below a micron. And then why is this useful? Because these modes, since the tilt is very small, they all live within the same beam, actually. You have a beam and not a plane wave because you also add this very slow amplitude modulation to everything, so that you have a well-defined beam, a wide beam. And since the tilt of these plane waves inside the beam is very small, all these components remain within the same beam traveling in free space unless you go to far field. Or if you want, you can use a lens that focuses at a given plane that corresponds to the far field transformation. In that case, if capital lambda is smaller than the beam radius, then all these components are resolved spatially, they separate, and you can eventually detect them separately. So this approach to encoding our discrete modes allow us a very convenient approach for somehow separating them when needed, while they are traveling all together in a single beam as long as you want to manipulate them all together. Another big advantage of this momentum encoding relative to orbital angular momentum encoding is that this is naturally 2D, because you can of course add a multiple integer of delta k along x, but you can also add a multiple integer of delta k along y. And you still have tilted plane waves, slightly tilted plane waves, traveling essentially along z until you separate them by a lens. So for example, this is a square lattice of in 2 dimensions of these modes, in which besides the average k position, I am representing also the phase gradient that is acquired by each mode due to these 2 terms here, using a color code for phase. So now, in our approach, let's see again what are the resources for quantum walk implementation. We have our n-level system, which is actually in general a 2-dimensional n-level system based on these tilted plane waves. Actually, more precisely, they are tilted Gaussians, but with a very large Gaussian profile. Our 2-level system are the 2 circular polarizations. The coin rotation can be readily obtained using any wave plate to affect the polarization, such as quarter wave plate, half wave plates, and so on. What is still missing is the coin-dependent translation. So we need an operator that somehow shifts the momentum of light, so it gives a transverse kick to the light, to the photons, depending on the input polarization. Something like this, that you get this phase factor and go from here to here, but you can also go in the opposite direction or this direction, depending on the polarization. Our approach to obtaining this is based on what we now call liquid crystal metasurfaces, which are devices somehow that can also be considered generalized Q plates. They are based on liquid crystal cells in which, in which you have a pattern of liquid crystal molecular director, which is the average orientation of the molecules, which also define the birefringence optic axis point by point. The pattern can be arbitrary and written in the manufacturing stage. In addition to that, by using voltage, we can control the tilt of the molecules in the plane, let's say out of the XY plane, and this allows us to control the retardation, the phase retardation of the birefringence. Now, in particular, the simplest approach to obtaining the quantum walk that I described is to use simple polarization gratings. We also call them G plates. Well, G stands for grating. Which have a structure like this. There is a molecular director orientation that rotates periodically along a direction, for example, along X, with a period lambda. And the optic axis is described by this simple expression. Delta k is again 2 pi over lambda, and you can also control again the phase retardation. What is the action of this kind of device? If you enter into such a G plate using horizontally polarized light, which is a linear combination of left plus right, in general, you will have that if the G plate is tuned to delta equals 0, it does nothing, so the light goes through, and then a lens focuses it to a central spot on a given detector. What you see here is actually data, and this is the spot that you measure on the CCD in this situation. Then you can turn on the G plate, for example, set delta 2 equal to pi over 2. In that case, you start to have some effect of the G plate, and what happens is that the left component is phase shifted toward left, and right, and the right circular polarization is phase shifted toward right, so that you get 3 spots. And then if delta is equal to pi, you have, let's say, full conversion, so that left's polarized light is entirely shifted towards left and the right towards right. This happens because you can see it in different ways. You can see it as a diffraction, a standard diffraction from a polarization diffraction grating. You can also see it as the effect of a geometrical phase due to this rotation of the optic axis transverse to the plate. And in this latter case, it's similar to the explanation that you usually have for Q plates. Now, starting from this concept and setting many of these G plates elements in sequence, you can have a 2D quantum walks that occurs in, let's say, entirely momentum space for light. And this was demonstrated by us in 2020 for the first time. We also demonstrated that it could mimic a topological system with certain topological behavior. You find the details in the paper. But what we actually implemented was an operator. The single step was implemented by using three elements. One was just an ordinary quarter wave plate, and then we had one of these translation operators along Y and another one along X using the G plates. Although we did also experiments in 1D in which we only had one of them, we removed the Y shift. So we have both experiments in 1D and in 2D. These are photos of the setup. This is a box containing several of these optical elements. All they are connected to a power supply to control the voltage, and they are put in a sequence with the light going through all of them. This, for example, was a 14 centimeters setup with 28 of these elements performing 14 steps. And what we got in the focal plane of the lens was the output, which look at like this. This is an experimental image in which several of these spots have been populated. And it's actually after only 5 steps of our quantum walk, and somehow connects our input mode with 121 output modes. Then we wanted to scale up these circuits. And the problem now is also to be able to apply this scaling up, having long quantum walks, to quantum light, not only classical light. So what I told you so far can be applied to classical lights or to photons. If you do that with single photons or few photons experiments, you rapidly run into a problem, which is losses. Even if it's in principle everything is transparent, you actually still have losses due to reflections, some scattering, some absorption. So if you have a train of photons, only some of them will pass by. And if you have n optical elements, this transmission probability is also raised to the n, where n is the number of optical elements. And if you send through this system many photons, say small n photons, then also the probability of having all n photons passing through scale as the exponential, as the power of this t to n raised to the nth power is also raised to the small n power. So it scales exponentially both in the number of optical elements and in the number of photons. So even if t is relatively large, this goes to 0 very quickly. And it's very hard to do experiments with multiple photons. So what we did is to work on compressing the quantum walk that I described to you, so that it could be done using only few optical elements. In principle, we approached the way to compress an arbitrary number of optical elements used to implement, for example, a given quantum walk into only one set with 3 optical elements. And this was demonstrated in 2023 using, as I told you, 3 optical elements. The price that we pay is that these optical elements are not anymore simple gratings, they are much more complex in structure. So, for example, this is the layout of our setup of the experiment published in 2023. This is a work led by Filippo Cardano, incidentally. And in this experiment, this was done in a classic regime. We had these 3 optical elements. And this picture down here are the structure of these 3 optical elements, where the structure is essentially the angle of the optic axis of these elements as a function of position in a false color scale. So you can see they are not simple gratings. And using a suitable arrangement of these three elements, you could mimic a full quantum walk of many steps. And in the output, again, we had the CCD, and this is the typical output. This was done in 1D, so it's only a line. And this line shows this agreement between experiment and theory. This is actually the equivalent of an evolution of 240 time step of a quantum walk. So you can see that many optical modes are addressed somehow. In principle, you are connecting one input mode with over 400 possible output optical modes. And the fidelity was around 85%, not extremely large, but already quite good. This was done using 1D. Then later we also did it in 2D, and this was presented more recently in the Advanced Photonics this year. Essentially, to do that, you need again a pattern in 2D of our liquid crystal metasurface, which is somehow complex. It looks a bit like this. This is one example, again in false colors representation. And this is the image, experimental image of this setup, of this kind of device you see in between cross polarizers, showing that after manufacturing, it looks a bit like this, with these structures which are periodically repeated and are rather complex. Then using three of these elements suitably patterned, you could get this kind of output, for example, of a 10-step 2D quantum walk, or even a 20-step 2D quantum walk. And this, in principle, connects up to 800 optical modes for the 20-step case, only using three devices in free space. Now, all this was shown in a classical regime, but we are now going really quantum. So we started to do experiments with a similar setup, but using, instead of classical light, using two photon states at the input. For example, generated by spontaneous parametric down conversion, a standard approach for generating photon pairs. Then they go through a similar setup as those I showed, and except that in the output you need something that detects single photons and is able to discriminate when the photons arrive at the same time, so that they are the same photons coming from the same pair. This requires to have a time resolved single photon camera, which is not trivial. There is a technology that we are using, which is shown here. It's a time-resolved single photon camera based on a photocathode. Then there is a multi-channel plate for somehow enhancing the signal, the number of photons. And then there is a sensor of light that converts them into an electric signal. And then a complex electronic system that somehow is able to time tag every photon, allow you to download all this, to detect all these signals, including the time of arrival. So using this approach, we started studying, before studying more complex situation, what a G-plate does. So a single G-plate, as I told you, when delta is equal to pi, it's full conversion, you only have two spots. This corresponds to having a single photon, for example, arriving in H polarization that is tilted slightly left or slightly right. But then suppose you have a pair of photons instead of a single one. If they are distinguishable, each of them does the same thing with independent probabilities. So you have that both photons can go left, both photons can go right, one can go left, one can go right, and vice versa. If the photons, however, are undistinguishable, even if they are initially distinguishable by the polarization, they are not anymore after scattering, after going through the plate, because if they go, let's say, both left or both right, they are somehow left or right again. Both of them are converted into the same sequential polarization state. So in this case, what happens is that so-called two-photon destructive interference, the same as Hong-Mandel effects, cancel these two possibilities. These two possibilities are cancelled out by interference. It's not a standard interference, it's the two-photon interference that can occur between two particles. is a completely quantum effect, cannot be mimicked by any classical mean. And then in that case, you still see two spots, but if you look at the time coincidences, they will never see time coincidences between these two spots. And this is completely different from what you have classically. So you see, for example, that the time distribution for the two photons, when they are distinguishable, shows a strong peak at the same time, where when they are not distinguishable, this peak is almost completely suppressed. And so we are now shifting this from two spots into a more complex four or multiple spot situation that you get at the end of our quantum walks, which corresponds to a quantum circuit defined by our specific unitary evolution. And we are studying the correlations of these photons that somehow can be rather complex, and that includes interference effects which cannot be understood with a purely classical approach. And now this is work in progress. So for today, I will stop here. Let me thank the group, and in particular Filippo Cardano, who is leading specifically this project, these activities. He is the main driver of what I presented today. Particularly the most recent work. This is the whole group. And let me thank you all, and Slava Ukraini.
Okay, thank you very much. And we have time for one or two quick questions, if anybody has a question. Feel free to raise hand or just shout it out.
Hi, I can probably ask a naive one. Can you hear me well?
Yes. Hello, Nina.
Yeah.
Nice
Hello,
to meet
Lorenzo.
you.
Yeah. Thank you for a great talk. So my naive question was, basically when you are showing these connectors of input modes to the output modes, how do you evaluate how good your circuit is working? So you were mentioning the fidelity. So I was just wondering, can you give
so far we are essentially measuring the fidelity relative to what we can compute classically using the theory of the quantum evolution. So how perfect is our quantum evolution relative to the theoretical one that you should expect. But of course, there are many more things to evaluate, and the most important step will be to gain reconfigurability, so the ability to change your network and to change it possibly in as large as possible set of possible connections. So far, we are rather rigid in this, so we need to go in that direction. And at that point, of course, we'll need other merit figures for measuring that.
Yeah, it looks indeed complicated, but yeah, very
Yeah, but there are
exciting.
approaches to go in that direction. I mean, there are approaches.
Okay. Maybe we'll move on since we're a few minutes behind. Thank you very much.
Thank you all for listening and for inviting me. Goodbye.
And our last presentation for the day before the poster session is Aristide Dogariu. And Aristide, if you're there. There you are.
And I'm here.
And I must apologize because I have to leave in about 15 minutes to go teach class.
Huh.
So it's nothing personal. If somebody else, if somebody wouldn't mind just giving them the 10-minute notice kind of thing, I would appreciate it. Otherwise, Aristide, you could just talk as long as you want.
Talk till we die. Yeah. Thank you, Greg. Thank you.
Oh, and could you change the view? I'm seeing the presenter view.
I see that. Yeah. Hang on a second. The second screen disappeared now.
Hmm.
That's a problem.
Yeah.
Are you seeing the same now, right?
Yeah. Oh, now I'm just seeing the main editing window for PowerPoint.
How about now?
I'm seeing the presenter view. I think you can go to display settings at the top to switch it. Yep.
Yeah.
We're done.
Now you're ready.
Okay.
So feel free to
It's
begin
not
editing.
good. Hang on. It's not good. I don't know why. Sorry. You are still seeing my
Yeah, you need to swap again.
yeah, but that's not good because I don't have access to the other one. Yeah. I don't understand why. Because I tried before and it worked.
The only other thing I could recommend immediately is quickly shutting down and restarting PowerPoint.
PowerPoint, yeah, that's probably. Yeah, I'm sorry for this, but
It's the modern world. Technology made everything work much smoother.
much better, right? Correct. Yeah. One second, please.
Mm-hmm.
I'm getting there. It's the same thing.
You could always just use the regular main PowerPoint window and not run it as a slideshow, or
Hang on a second.
all right.
I want to. So what do you see now? Is the same as before, right?
Yep, we're seeing the presenter view,
Yeah.
which also, and there we see the main slideshow.
You see the slideshow, but I don't have means to at least you have a little bit of here. All right, so we'll go this way.
Okay.
So sorry for this. What I was. Yeah, you see the slide. I don't know how to advance it. Okay. All right, so we will try to talk in the remaining of the time about sensing. In other words, the transfer of information from a place where a phenomenon of interest happens to the user, and this natural phenomenon of sensing is actually a more complicated process, and this process involves of course, it has a task, relies on a phenomenon that needs to be to happen to generate a signal. We usually describe a sensing process as being a deterministic one in which the signal is perceived as being uniquely describing the information that I want to get. And in the way real sensing happens is that this deterministic ideal occurrence is only very seldom encountered. In building up strategies for getting a better sensing outcome, a better result, we usually take advantage of prior knowledge, right? So we did not start the world. People have been before us. So there are task priors, there are signal priors that we usually take advantage of. Moreover, there are situations where these unavoidable signal fluctuations are the ones that actually carry the information. Therefore, the strategy that we put forward for the process of sensing should aim at purposely enhancing and controlling the fluctuations of the signal. And I'm going to show you a few examples of that. Now, in deciding which kind of procedure I'm going to follow, I need to take into account every time what I would call the sensing budget. So any kind of sensing process, either a active process in which a field is incident on the target and something is detected as a result of that interaction, or electromagnetic fields are generated by the target itself. In either of these conditions, one has access to alternative ways of producing the result of the sensing. For instance, I can put my money on the source, making the source of the excitation of the target complicated, and then in the of course the most information can be recovered by having a complex detection. However, for sure that would be an expensive proposition. Ideally, I would like to have in our situation, because we are talking about structural fields in this community, I would like to take advantage of ability to structure the field to allow me to get a good result with a very simple measurement. And this will be the philosophy that I'm gonna show you a few examples of how procedures could be developed in this context, right? So we have a controllable, seemingly more complicated excitation and a simpler measurement. The most rudimentary example of this procedure is eliminating a scattering potential with an adjustable, spatially coherent field, right? So this is having a field that is a partially coherent in spatially is probably the simplest way to think about a structured field. To create it and control it, all we need to do is to essentially manipulate intensity distribution across a generic spatially incoherent source. By doing this, you essentially scan the coherence function of the field through the scattering potential that defines your problem, and from the intensity fluctuations detected with a very simple detector, like I promised before, one can recover the scattering potential of the correlation of the scattering potential of this interacting target. You can do even more. You can structure the same type of spatially controllable spatial coherence in a three-dimensional setting. You create a three-dimensional controllable source of partially coherent fields, which allows you to probe the correlation function of the scattering potential across this hemisphere with a precision that is better than the wavelength, based on simple intensity detected in the far field. So this is a very good example of a complicated source, spatially incoherent source with an intensity modulation, and a very simple detector to achieve performance that normally requires to be in the near field of that target. You can do even more in the context of so we heard something about the analogy between classically partially coherent fields and entangled fields. Don't want to get into any details, but the analogy is it's essentially perfect for the scope that we are addressing here. You have an object, you have a reference, you can call it idler, and what you measure is essentially an intensity fluctuations, the famous G2 factor. But the fact that you can manipulate the spatially coherence of the source allows you to actually manipulate even the phase of the coherence function of the field that eliminates the object. So if you manipulate the phase of the interacting field with your target, you can recover something that in the quantum counterpart you cannot. You can get actually the phase of the object that you interact, right? So this is a cosine target, a cosine grating that is manipulated, and you can get the positive and the negative phase by translating that target. So this is a few examples of the rudimentary, what I would call rudimentary structured fields. Let's see another type of structured fields in which one can have access to individual discrete realization of the field. Before, we had access only to the ensemble average of these realizations. But now, if I have access to individual realizations, I can produce a discrete correlation between the excitation field and the recovering target. And that allows me to image with a very good compression ratio. Mind you that this is not a CCD camera. This is just simply a fluctuating, a pixel intensity detector, point detector. And you can do imaging of this nature based on this correlation at extremely low excitation levels. So this is the image that you recover with it's basically a target to the reflectivity of 0.2 that is recovered from excitations, each of it having on average 1 photon per excitation. So extremely low light levels. So this brings us into the realm of certainly biology, right? So this is an example of the robustness of propagation, because now the excitation fields is essentially spatially random, is not one of those nice regular Hadamard patterns, and that induces certain degree of robustness against propagation, and allows you to actually recover information from both the spatial correlation function of the signal, from the fluctuation of intensity, the so-called Fano factor. The sparsity of these targets is not critical. It works equally well for symmetric and asymmetric on average, asymmetric random targets. Again, you do not recover an image, you recover an average property, an average length that characterizes the this random scattering potential, if you wish. But so this is recovered by having access to the each realization of the randomness. But let's suppose that you do not have that. So you want to make it even tougher on yourself. The only thing you know the first and the second moment of the intensity distribution of your illumination patterns. So this is a stochastic illumination in the main meaning of this stochastic process. So I have a random process, eliminates a random target, I detect fluctuations. From fluctuations, I can get first, second order moment, and so on and so forth. Of course, the first two moments of a distribution, and this is not limited to the first two moments, but I'm just giving you an example here, are rather robust against additional perturbation that may happen in the way in and the way out towards the target. So let's see what happens. So this is the distribution of the scattering potential. It has a characteristic length, and this is what I'm after. I'm after the average size of these dots, which represent the correlation length of the scattering potential in the plane of the target, and I produce random illuminations on it and record fluctuations. If I record the fluctuations, I can evaluate the Fano factor of those fluctuations, and then I practically change the size of these dots, and at some point when the characteristic scale length of the illumination matches the one of the scattering potential, there is a stochastic resonance from the position of which I could identify essentially the correlation length of the scattering potential that I was after. So this is, in my mind, a clear example that one's trash is somebody else's treasure. Random fields are not necessarily a nuisance. They can be used for a good purpose. I'll give you a few practical examples of this type of measurement. This is a scale measurement, a linear measurement done with an extremely low signal-to-noise ratio. This is the scattering correlation length in a cell culture that is exposed to an extremely low level of light. So this is really the non-invasive nature of any kind of biological sensor. Based on these on the similar concepts, one can monitor very easily modifications in the structure function of the scattering potential. In my interest here is the structure of the cells that are actually scattering the light, and so on and so forth. So let me speed up a little bit. So far, we use some kind of unorthodox structured light. Of course, there is an entire zoology of structured light created for different purposes and reviewed in a number of papers. We will pick on for this audience. Probably we should. Is no need to discuss the benefits of actually using a structure being a Bessel-like beam in the context of scattering. I'm going to show you one example of this kind of use. Let's suppose that you are trying to measure thermal fluctuations at the interface between a gas and a liquid. Conventional measurement sends a beam. This is the K-space explanation. Sends a beam here, recover it here. This is the Fresnel reflection from the interface, and the scattering manifests through a dispersion of the K vectors and of the scatter field. So to take an average of a good robust average measurement, I need to move around my detector here. If I use one of these structured fields, then I have the benefit of measuring in the center with the same momentum transfer an enhanced signal, because all of these plane waves contribute to the same detected signal. The signal will be enhanced. And by the way, the signal to noise is certainly superior because it's a zero background measurement. And we applied this to the interface between water and water vapors with a azimuthally polarized one of these Bessel beams. This is the experiment. Nothing interesting about the components, but the fact that we can essentially measure from far the small fluctuations of the water interface. It is unique. So there are different models for this water vapor interface. I'm not going to go into any details, but the thermodynamics of this layer is rather interesting. There are molecules which actually are in the process of evaporation, other molecules in the process of condensation. Some of these processes depend on the temperature of the liquid, some do not. So it's a highly non-equilibrium problem, and this method allowed us for the first time to practically identify. Let me just jump to identify the very subtle details about this non-equilibrium. In other words, how you actually heat this surface. So between ability to measure thermal fluctuations at the interface and ability to discriminate where the actual source of heat lies with respect to that interface, it was something that only this type of probing allowed us to do it for the first time. Now, let me briefly show you another task. So how can one tell a shape? You can excite the shape changes, you get fluctuation in intensity in different polarization channels, you solve an inverse problem, and eventually you discriminate a shape by recording many realizations of this orientation of the shape. But how about if the situation is more complicated? You have more objects, more anisotropic objects. What do? You can not examine them, and let's suppose that you cannot examine them one at a time. So a solution is to actually isolate small volumes of this environment with anisotropic particles and enforce non-Gaussian fluctuations in the scattered intensities. And the way we do this, we isolate two adjustable volumes which are excited with orthogonal polarization. This is a clear space polarization entanglement, as we heard before, and measure intensity fluctuations as a function of the ratio of those two volumes. This can be very easily implemented with the infamous by now Axicon optics. and a polarized measurement of this G2 temporal fluctuations allows you to discriminate. And let me just stress this: allows you to discriminate the between a isotropic shape and an anisotropic shape with a very tiny anisotropy. This is a sphere. This is an ellipsoid with an isotropy at 1.8. So this is just a very, very gently pressed sphere at concentrations of 10 to minus 8 by volume. So this is a very very accurate and very, very sensitive measurement, which is enabled by the ability to control the field distribution through this scheme, right? And yeah, these are regimes in which normal microscopy, diffraction measurements, or even spectroscopic measurements cannot really operate. So we really take full advantage of ability to control the structure of the illuminating field. Another example: you have a target embedded into a highly diffusive medium. It's highly diffusive medium. The actual depth is 10 mean free path. So the only 10 to minus 9 photons reach and detect this level. However, 13% of that might have reached this level. So question is, how do I detect the presence of such a target? This is a very important problem in both water and non-water. So what we do, we take advantage of this coherent phenomenon, right? This is enhanced backscattering. I don't think I need to explain the coherent interference between counter-propagating waves and so on and so forth. The idea is that now, if you use as an excitation a source for which you can manipulate the phase distribution, and the most convenient source for that nature would be an OAM beam with adjustable topological charge, you will see that practically the magnitude of that enhancement, coherent enhancement, decays when the phase variety, the phase distribution becomes more correlated over smaller separation distances across the object, and that one allows us to practically identify the optical, with a very high precision, the optical thickness of this layer, and therefore identify targets, reflective targets, which are embedded down to 36 mean free path. So practically this is a completely opaque medium that is penetrated by coherent light, and taking advantage of the subtle phase correlations in the incidence, you can practically measure the thickness of this medium. Important in using these type of structured fields is the fact that they are really very easily to be deformed, right? This is a blessing in disguise. The fact that I can structure the field so exquisitely, because on propagation it actually destroys with a rate that is carrying information about the medium, right? So between a deterministic field and a fully developed field, there is an entire range of optical propagation conditions. Now, I'm not going to get in, I don't have time to get through the details of how we model this increasing strength of propagation. But what I can tell you is that we can evaluate an average vorticity, an average orbital angular momentum as a function of conditions of propagation. Therefore, identifying the strength of the perturbation in terms of both spatial correlation and probability distribution of the phase, and come up with values on the propagation distance for which the initial vorticity, initial vorticity is practically maintained, right? So practically we have identified a memory of this means to measure the memory of these orbital angular momentum beams, and that allows us to practically approach an inverse problem. So this is an example where we had an adjustable, thermally adjustable perturbation, and measured the extent of this memory of optical vortex beams as a function of strength of disorder and the spatial correlation of disorder. One additional topic of interest is to really understand at the basic level how this perturbation practically evolves, and I'm going to show you that there is much more to understand about this, and this is a source of information that has not been tapped in yet. So our question of interest is how do vortices originating on the optical axis evolve? That the difference in we have two types of vortices. Let's stop. So you have a vortex beam, you have a perturbation, that beam degrades, and a lot of tons of singularities develop. But there are two categories. There is one class that evolves from the initial one, and there is the other class that is typical to Gaussian fields, that the canonical optical vortices that have been looked at for a long time. Now, for the lack of better terminology, we just call these things thermal vortices. These ones are main vortices. Now, we can evaluate how the main vortex, right? So if you have a topological beam with charge 1, the evolution of the vortices originating on axis follows a diffusion-like process. However, is not a real diffusion because of the influence of the vortices that lie outside the first zeros of intensity, the first ring. So the process is not a normal Einstein-like diffusion because of the interaction with thermal or secondary vortices. And as you see here, the actual probability density function of the distribution of locations after some propagation is not really a Gaussian, but is more like a Rayleigh distribution, therefore carries information about the type of potential that destroys their location. So you can measure the distribution of that in the when you have one single vortex, but the most interesting part is when, for instance, you start with the topological charge 2. Then you have two individual vortices that practically interact with each other, and they have the same charge, right? The canonical vortices are always produced and annihilated, right? Producing pairs and annihilated in pairs, but these ones have the same charge. So there is actually a vortex-vortex interaction, like charges of the same sign on top of a background random potential, and this is the information that can be speculated to identify the location, or in this evolution map, the strength of the scattering potential that has produced, or that has broken the initial phase distribution of the beam. So if we this is a now that we know how the vortex beams are practically broken into transformed into a essentially spatially incoherent beam, then probably we should look more carefully on the properties of that random field that is generated to use it for our sensing purposes, right? Turns out that these kind of perfect optical vortex beams, right? So this is nothing else but the Fourier transform of the vortex beam, right? And it's depending only on the topological charge, manifest a slowly evolving spatial coherence and manifest a very different k-vector distribution, and this is what we are speculating for both imaging and other kind of sensing that I'm gonna show you in a minute. So we have looked at this kind of thing in great details in the statistical properties that certainly go beyond second order, and as you can see, and based on the fact that you can manipulate both the spatial and the k-space of these fields with the type of vortex beam that you are actually starting. So therefore, a complete description of whatever happens here must involve the Wigner formalism. So based on that, we can demonstrate a very fast imaging of hidden objects. So you have a hidden object between two disturbances, and you take an image behind that. You have an additional image without the target. You evaluate from this what would have been the initial incident field on the target, and when the dust settles, you have enough information to recover images of this nature with varying accuracies depending on the initial topological charge of the beam. You can adjust the sensitivity to anisotropies in the target and things like that. I know I'm rushing through this, but I'll be very happy to talk about details of this. And I have two more things to tell. The fact that you have a discrete basis for these random fields, namely the topological charges of these fields, allows you to actually create and use discrete correlations between scattered fields. So this is an example where this strength of the correlation between as a function of delta m, the difference between topological charges, is sensitive and can be used to determine the optical properties of this disturbing medium. So all you need to do is to change the topological charge of the medium, record scattered fields, and from there you can infer the strength of this disturbance, the scattering mean free path of this disturbance. And lastly, I will just briefly tell you that having access to controlled optical properties of the field, both in terms of the spatial distribution and the k-space of this seemingly random field, allows you to control allows you to control the conservative part of an externally applied field in an active control of light on matter, and practically look at artificial thermodynamics problems that can be uniquely controlled by this ability of manipulating the topological charge. So this is, for instance, an example of effective the effective potential in which a particle resides. So if there is no field, it's in a thermal potential of 1 kBt. You apply a Gaussian field, Gaussian random field, the particle is essentially pulled down. So this is an incipient laser trapping in a random field. The effective temperature decreases. Now you apply a random field generated by beams with different topological charges, and you decrease that effective temperature even more. This is a consequence of the fact that the effective potential that is imposed by light here is certainly steeper. And it's steeper because of the k-space distribution that is associated with random fields. Of course, as you go to higher and higher topological charges, this effect, due to the randomness in the field, gradually disappears, right? So this is a very different type of application of these fully controllable random fields. Now, in summary, I think I showed you a few examples. Hopefully, I convinced you that tailoring the properties of light open new and very different opportunities to manipulate matter, to sense and things like that. And in most cases of interest, the effectiveness is limited, but again, there is a blessing in disguise, because the degradation of these properties is a process that carries information about the medium that the light interacts with, and therefore can be speculated in an inverse problem. And this stochastic interaction phenomenology really can be the basis for robust environmental sensing, like I showed you a few examples. And with this is a summary of the snippets of research that I listed today, all of them under the umbrella of structured optical fields, originating from purely stochastic concepts, or as a result of interaction between a deterministic phase controlled beam-like field and the unavoidable randomness on propagation. And with this, I thank you very much. These are the people that have been involved in these projects, and I will be very happy to take any questions. Thank you.
Thank you very much. There are no questions. Thus, I would like to thank you for your great presentations, very expressive presentation. And it was our last presentation today, last oral presentation. Now it will be the poster session. It will start it is starting now. You can join the links poster session. All of the links are active. Thus, thank you very much once more, and we continue our work tomorrow at 9 o'clock with the second day of the conference, Singular Optics Day. Thus, see you tomorrow. Thank you very much.